All right, next we'll talk about a little bit more complicated example of this 3N analysis. Um, we have um, trans-1, 2-dichloroethylene. So this molecule going to look like this. It belongs to the C2H point group. It has a C2 axis right here in the center. It doesn't have any vertical mirror planes, and it does have a horizontal mirror plane. So this is the C2H point group if you go through the process and assign it. So anytime you're given a molecule, what you want to do first is make sure that you're orienting everything correctly. And for all of the different point groups, whatever the highest rotation axis is, it's assigned as the z-axis. So as I've drawn this molecule right now, the z-axis would be coming out of the page and into the page, and this molecule would be laying in the xy axes. So it's actually good to annotate that way. So to orient it properly for you. Okay, the z-axis goes right through the center of the carbon-carbon double bond. Hydrogen, chlorine, chlorine, hydrogen. Okay, and so then there would be our y-axis and our x-axis right there. Okay, always good to put some notes for yourself. Molecule lies in the xz plane. There will be times where you get a choice about how to orient it, how to orient the molecule. The only thing that will cause a problem is you cannot change your mind partway through the process. So in this case, we're actually stuck. It has to be the XY plane that we orient the molecule in. Some more complicated, for example, the D2H point group, we would have a choice about which way to put it, but we just couldn't change our mind partway through. Regardless, you want to make some really good notes for yourself about how you have oriented the molecule. All right, then to do this analysis, so we go and we put a little coordinate system on each of the atoms. I can't really without making it too messy, so I'll put that coordinate system next to the atom. Don't forget my carbon atoms. Okay, so there's 1, 2, 3, 4, 5, 6 atoms total. Okay, so 3n equals 3 times 6. So there's 18 total motions that this is going to have. 3 translations, 3 rotations, and 12 vibrations. Okay, so once we've done that, I'll make a little model of my character table here. C2 along the z-axis, inversion, and sigma h. Okay, and this is my reducible representation that I'm working out. Okay, so the first one, of course, the boring one. Each of the 6 atoms has a set of vectors. The vectors, of course, are unchanged because E doesn't do anything. So it has a character of 18, so it has to. All right, next, there's a huge simplification that happens when we do this. So if we do a symmetry operation, if all the atoms move from their current location, then the character is 0. We don't have to think about what happens to the little sets of vectors because the atoms themselves move with this operation. This C2 axis goes right through the middle of the CC bond. It doesn't actually touch any of the atoms. And so when I do this rotation, all 6 of the atoms move. So since all of the atoms move, I don't even have to worry about the vectors. It ends up being a character of 0. All right, inversion. does the same thing. It swaps the 2 carbons, swaps the 2 chlorines, swaps the 2 hydrogens, so it's also 0. So the middle of this is pretty easy. Then finally, the sigma H is going to be the hardest one. So for sigma H, all 6 of the atoms are in the plane, so that means they're all going to count. But things are going to happen to their sets of vectors. And so if we look, I'll just draw one little set of vectors here. If I have z, y, and x, and I do a sigma h, which is the xy plane, x is left alone, y is left alone, and z goes into the negative of itself. So z, which was pointing out of the plane, points through the plane now. So y is left alone, x is left alone, z goes into the negative of itself, and this all sums together to be +1, -1, +1 for a character of +1 per atom. So how many atoms are there? 1, 2, 3, 4, 5, 6. 6 times +1 gives me a character in the reducible representation here of 6. All right, so still have more work to do. Now we're going to reduce this reducible representation, and it's going to be some S-O-M-E, sum, S-U-M, of these irreducible representations. Let's follow what Carter does in his book. He uses this worksheet method. Okay, so I'm basically taking right now and just modeling the character table. And then over here I add a couple of things. So I have this sigma. That's going to be, I'm going to sum these whatever numbers I get here. And then this sigma divided by 4 is the last thing that I'm going to do here. Why am I dividing by 4? Because there's 1, 2, 3, 4 symmetry operations. So I go in and I divide that sigma by 4. All right, so this Carter method that I really like, it's always best to first do this AG representation. So 18 times 1, because there's one of those, 18 times 1 times 1 gives me 18. 0 times 1 times 1 gives me 0. 0 times 1 times 1 gives me 0. 6 times 1 times 1 gives me 6. 18 plus 6 is 24. 24 divided by 4 is 6. Okay, then from here, we're going to go through and we're going to follow the pattern of this character table. And E is going to be easy. So the character table goes 1, 1, 1, 1. So we're going to go 18, 18, 18, 18. This one's going to be easy because anything times 0 is 0. Same for here. And then here the pattern goes 1, -1, -1, 1. We're going to go 6, -6, -6, 6. Now I'm going to do my sum. 18 minus 6 gives me 12. Divided by 4 gives me 3. 18 minus 6 gives me 12 again. 3. 18 plus 6 gives me 24 again for 6. So this total of this is 18. Okay, and that's what it needed to be. That's the 3n motions. So 3 times 6 is 18. These need to sum up also here for us to 18. Okay, just writing out what we worked out. So the reducible representation is composed of 6 AGs, 3 BGs, 3 AUs, and 6 BUs. Okay, this is 3N thus far. So I am going to now subtract out first the translations. This is the translation of the whole molecule. And those are worked out for us. So translation along Z is AU symmetry. Translation along X is BU. Translation along Y is BU. So I am going to subtract 1 AU and 2 BU. 1 for X and 1 for Y. All right, what I have left to subtract out, the rotations, those also have been worked out for us. An AG for rotation around the Z-axis, a BG for rotation about X, and a BG for rotation about Y. So minus an AG and minus 2 BGs. Okay, we've taken every motion, which is translation, rotation, and vibration. We subtracted out the symmetries of the translations, the symmetries of the rotations. And so what is left is the symmetries of the vibrations. So for vibrations, 5AG plus BG plus 2AU plus 4BU. So 6 and 6, that's 12 vibrations. 3n minus 6, 3 times 6 minus 6, 12 vibrations is what we expect for 3n minus 6 vibrations. All right, we still have a little bit more work to do. So if at the end of this we want to know how many of these we could possibly see in the infrared spectrum, we have to go back to our character table. And for a vibration to be infrared active, it has to be one of the irreducible representations that contains Z, X, or Y. So only the AU and BU vibrations are infrared active. So AU and BU. Okay, so this 2 plus 4 gives me 6 IR active vibrations. Okay, so there's 12 that are happening, 6 and 6, but 6 of the vibrations are invisible to our infrared spectrometer, and 6 of them are visible to our infrared spectrometer. So best case, we could see 6 IR bands for this molecule, again, which is trans-1, 2-dichloroethylene. I say best case because it's possible when we put this in solvent or whatever. So 2 of these might overlap. And so rather than seeing all 6 clearly, we might see 5, or we might see 4, or one might appear as a shoulder of another one. So we expect that at most we're going to see 6 infrared active bands. When we actually go to the lab and run the experiment, it's going to be 6 or less that we see.